The factory floor is inherently fluid. When blending a specialty sauce, industrial vats deal in continuous volumes, evaporation, and physical weight. But enterprise logistics require absolute data precision. Tracking liquid yields, specific ingredient ratios, and the transition into discrete packaging requires a predictive digital twin of the factory floor. Historical logging after the fact is insufficient to prevent a line stoppage. The Qmuzik platform provides the framework to translate this physical compounding process into a rigorous digital architecture. Building this architecture requires 3 distinct phases: defining the static recipe, calculating the dynamic material requirements, and executing the physical batch. Success across these 3 phases ensures that every physical batch is backed by a precise data trail, allowing the enterprise to minimize material shortages and maintain exact batch costing. This flowchart illustrates the central processor, Material Requirements Planning, or MRP. It constantly ingests current systemic conditions, monitoring inventory levels, safety stock thresholds, and customer orders. After calculating these variables, the engine generates actionable signals: procurement for raw materials, and production for internal manufacturing. While Qmuzik's interface has evolved from legacy desktop environments to the modern cloud platform, this underlying data architecture and the calculations driving it remain identical. However, before the MRP engine calculates a single requirement, it requires a flawlessly defined structural baseline. That baseline is the bill of materials. A bill of materials is a comprehensive inventory of the raw materials and quantities needed to manufacture an item. In Qmuzik, this is defined as a product structure, the exact proportional recipe required to yield a specific batch of finished goods. This is the legacy desktop interface used for maintaining these structures. The core logic involves establishing a strict parent-child relationship between the final product and its raw components. In the modern Qmuzik cloud interface, this exact relationship maps directly to the web-based maintained parent configuration. Here, the target batch is selected as the top-level parent. This grid displays the linked child components required for the parent batch. Every ingredient has an exact base unit of measure, like liters or individual bottles. The quantity per column dictates the exact consumption ratios, allowing Qmuzik to lock down the required inventory. The product structure is the axiom of the ERP. If the digital recipe is flawed, the system will direct the shop floor to consume the wrong materials, ensuring an expensive failure on the production line. With the recipe locked in, the MRP engine is initialized to evaluate the physical inventory against the requirements of the bill of materials. This interface shows a targeted selective MRP run. While a global run calculates the entire enterprise overnight, a selective run isolates a specific target batch to immediately check the feasibility of producing it. The parameters established in the legacy desktop setups operate identically in the cloud environment. Planners can instruct the engine to strictly exclude certain stock statuses, like quarantine or awaiting repair, from the calculation. During execution, the system processes each level of the bill of materials. It iterates down through the parent assembly and calculates the gross requirements for every linked child component. This log provides direct feedback on the run. It details the exact sequence of processing levels and flags any data anomalies detected during the calculation. The MRP engine has now transformed a static set of structural rules into dynamic, time-phased signals for procurement and production. For manufactured items, the output of that MRP run is a planned order. When authorized, it is firmed into an internal order. An internal order, or works order, is an internal document authorizing the manufacture of a specified quantity of a product. This is the internal order header in the cloud interface. It assigns the planned production to a specific organizational division and designates the individual planner responsible for the run. Beneath the header, the order breaks down into specific line items dictating which components must be pulled. Every line carries critical constraints: exact ordered quantities, expected yield accounting for calculated scrap, and a hard completion date. This digital authorization is what finally allows the physical execution to begin once the schedule hits the factory floor. The internal order acts as a strict blueprint. It prevents the shop floor from arbitrarily pulling costly raw resources without documented intent and systemic oversight. With production authorized, the system relies on movements to track the physical execution. Movements are the system transactions that cause a change in the particular quantity of stock on hand, maintaining parity with the database. The first step is issuing raw ingredients from the physical warehouse into work in progress. Work in progress, or WIP, refers to partially finished goods currently being processed on the factory floor. This is executed via a stores-to-order requirements transaction. The user specifies the exact source location in the warehouse and the precise quantity to deduct from inventory and assign to the batch. This systemic deduction mirrors the physical reality on the floor. The raw ingredients are now being actively consumed by the mixing vats. Once the batch is bottled and finalized, a closing production-to-stores movement is executed. This yields the new finished goods back into the system, increasing the available inventory of the final product. Without disciplined, timely movements, the physical process outpaces the data. The digital twin fractures, resulting in ghost inventory on the shelves and catastrophic miscalculations in the next MRP run. With the production cycle physically closed, the final step is systemic verification. Planners must ensure the data has settled correctly across the enterprise. The Inventory Analysis Dashboard is the primary lens for this audit. It displays exact stock levels and precise physical locations in real time. This dashboard allows users to rapidly filter results, adjust parameters, and export the data to cross-reference against physical cycle counts on the warehouse floor. This visibility confirms that the newly yielded batch of sauce is officially logged and available for allocation. Real-time inventory visibility prevents accidental overproduction of stock you already have and exposes hidden bottlenecks in the warehousing supply chain. The ultimate test of the production cycle is how it impacts the broader enterprise. This is viewed through the supply and demand function. This list confirms the resolution. The completed internal order has increased the available quantity, balancing out the open sales requirements and resolving the initial systemic shortage. The workflow started with a precise product structure, mapping the batch recipe. That recipe was processed by the MRP engine, generating actionable internal orders. Finally, it was executed through disciplined inventory movements, tracking the flow from raw stores to finished yield. By integrating structural rules with real-time inventory movements, Qmuzik allows a manufacturer to anticipate supply needs and maintain precise quantities required to meet customer demand.